Early on in a project, I like to start reasonably abstract and to try to infer from the physical world some general principles for the topic at hand. And so one of the topics I'm working on is on modularity in electronic healthcare records, trying to understand what modularity means. And so this presentation will collect about 5 of the general observations and themes about modularity in the physical world. And the summary is that pretty much the entire physical world operates using modularity. The world really would not function without it. There's small touch points and interfaces that bring together these different components, and it's these interfaces where you in particular need to have standards and specifications. In retrospect, this is all quite obvious, but it's nice to have all these 5 observations in one place, and it provides a good starting point when thinking about the design of modular systems. And this image that we're looking at here is a picture from the 606 Universal Shelving System by Dieter Rams. So, observation 1. Almost everything in the world involves modular components. If you look around you, almost everything is relying on modularity to function. The building that you're in, almost all the components are from standard stock lists. The dimensions of the wood, the steel, the doors, the windows, the stairs, the glass, they're probably all based on standard increments with standard maximum sizes. And it's not just the construction of the physical building, but the actual objects around you. If you pick up an electronic device, you'll find the components inside are sourced from multiple suppliers who all sell components with standard specifications. The materials on the clothing that you wear follow standards to make sure that when manufacturers source wool, that it's the same from different mills. If you go to the hardware store, a computer store, an audio store, an auto repair store, these all sell modularity. And these are self-contained objects that can be brought together. If you think when you go into Home Depot, you're essentially just walking into a whole world of modularity. And modularity is nested. Small modules, such as screws and plastics, are brought together into larger modules, such as telephones, and then those objects are brought together into larger modular systems, such as phone networks. And so, of course, you don't have to use the standard components, but I think one of the important things to realize is that if you don't use standard modular components, you're going to incur additional cost and additional time. And so, really, modularity allows us to construct and build our physical world quickly and cost-effectively. It allows for efficient and effective distribution of labor and resources. It helps drive competition in the marketplace and innovation, and it's really critical to life. And of course, modularity isn't limited to the physical world. It's observed in biology, in chemistry. The atoms assemble into molecules and into the elements of the periodic table. Cells, organelles form into cells, which form into tissues and then organs and organ systems. It really is a fundamental organizing principle of biological life. And the same is found in music, art, architecture, philosophy, you name it. The world relies on the assembly of fundamental modular pieces into larger aggregate groups. And so the main summary for observation 1 is that nested modularity is a fundamental framework of the organic, industrial, and metaphysical worlds. And of course, then the question is, should we not strive to have the same modularity built into our digital world? We move here into the second observation, which is that you need to understand the module's borders and boundaries. Modular components have borders and boundaries, and sometimes this modularity is bound within an internal system, and other times modularity fits into an external system. And each of these requirements for its boundaries will be different depending on the goals. So if we're looking at modularity within an internal system, you could look at systems furniture. And so in the 1950s, modular furnishing took off. There were systems of components that could be assembled by the homeowner. Today, you might think of this similar to IKEA-type furniture. But at the time, you had, for instance, Dieter Rams in Germany working on RZ57 and then the later 606 system. You had Hans Gerlot in Zurich working on the M125. And you had Charles and Ray Eames in the US working on the Eames storage units. And this was all going on in the 1950s and 60s. But each of these modular furniture systems were designed to have extreme flexibility within itself, but there was not flexibility between systems. And of course, part of the reason that modular furnishing took off in the post-World War II era was that it allowed the ability to have high-quality, low-price furnishings with individuality. Now, when contrasting modularity within a bounded context, you could look at modularity with a lot more flexibility. And so one example might be movable type systems. So one of the great geniuses of Gutenberg in the printing press was the separation of the printing pad and the movable type. Before movable type, printing systems used stamps or wooden blocks that were inflexible in offset printing. But the ability to cheaply produce new metal-created typesets allowed the execution of book publishing very quickly. And so that these types could be joined together and then used on different machines. Now, of course, the type height varied from country to country, and that reduced modularity, but the general principle holds that an important consideration when designing modularity is the boundaries and borders of the modular components, and consider the extent that that module needs to work either within an internal system or within a larger external system. The third observation is that modularity has well-defined small touch points and interfaces. For instance, think about how all these different modular systems come together. Whether it's the light socket, the plumbing socket, or the screwdriver, they all have standard connections, which are generally very small surface areas given sometimes the size of the other modular systems. Even the system of writing, you have the module of the pencil being joined to the module of the paper, and this is being joined with the module of the human. And you can change out any of these three different large modular parts, but they're overall intersecting at a very small touch point, which is the pen on the paper and the hand on the pen. Or a screwdriver, it has a handle and a drive tip, and the handle has incredible modularity in the materials, the cost of design, its length, its automatic or manual, whether it's ratcheting or not. And then this handle is solidly connected to the drive tip. And again, there's huge variation here, whether it's magnetized, how long it is, the choice of materials, and choice of tip shape. But when it comes down to the actual drive tip shape here, this small part of the screwdriver is highly standardized and specific, and that's because it's the touch point and it's going to interface with a whole nother modular system. One sub-consideration is that these touch points between modular systems evolve and converge over time. And so something as straightforward as the audio jack or the phone jack underwent considerable evolution and convergence over the last century, different sizes, lengths, versions, and capabilities. And older audiophiles will talk about in the past being unable to connect different parts of their stereo system together. And that's because the different manufacturers use different inputs and outputs. Now, the same can be seen with computers in the 1970s and 80s, where components such as monitors and peripherals were proprietary to the manufacturer because common connections and plug-and-play capability evolved later. Or you can look at video cards. Again, in the 1980s, you had the older monochrome displays and the newer color graphic video cards, and you would have to manually adjust the dip switches between these in order to create interoperability between them. And there's many other examples of diversity and convergence upon touch points. Consider the videotape wars between Betamax and VHS, the DVD wars between DVD and HD DVD and Blu-ray. Convergence doesn't necessarily follow the best technology, but it's this complex interaction of wider market forces. And the third of these sub-observations about touch points is that a touch point requires a minimal standard, but you can exceed it. And so if you consider a piece of gym equipment that connects a cable piece of gym equipment to a handle, there's the module of the handle and the module of the cable system. And these two large independent systems are connected by a very small touch point, which is the standard D carabiner. And so we see an example of that clamp right here. And as long as the manufacturer of the gym equipment and the manufacturer of the handle ensure that the loop on their equipment is at least over 1/2 inch wide, they'll be able to accept most of these carabiners, and therefore they'll be able to have connections between these modular systems. But this is just the minimum. You just need to be able to pass this type of carabiner between the two. There's nothing that stops a manufacturer from exceeding the specifications and designing their loop to be 1 inch wide, for instance. In this case, you could consider its full backwards compatibility. Just another example here of the original IBM parallel printer adapters. Back in 1981, it was proprietary to just IBM printers. And then over time it evolved, and then in 1991 you have the Network Printer Alliance forming. And then by 1994, after more standardization, after innovation, IEEE released the IEEE 128.4 standard, which had new port settings which were 50 to 100 times faster than the original port. But despite far exceeding the original port, they still preserved full backwards compatibility. And so the summary for this observation about these small, well-defined touchpoints and interfaces is when designing a modular system, you should both consider what these interfaces and touchpoints are and how they may evolve over time. We come to observation 4, which is about standards and specifications and how they really make the world operate and function. A critical part of understanding why modularity works in the physical world is because of the magic of standards and specifications. A specification is something that outlines how something should be done, either such as a process, how it should occur, or how a product should be built. This is often a document internal to an organization, and a specification might reference a standard. And standards are formalized documents that help have, quote, uniform criteria, methods, and processes and practices which may or may not be requirements. And so you've probably heard of standard bodies within your nation, which have standards which you have to meet, for instance, as a law society or as a medical society or as a manufacturing society. And a lot of these national standard organizations are part of larger international standard organizations, of which, of course, the biggest is ISO. And standards accomplish 3 critical tasks. The first is compatibility. They make it so that products can fit together. So the reason that your credit card operates is there's standards for its physical size, there's standards for the communication protocols. Standards also help, secondly, with safety. And standards will describe the safe way to produce something or the safe way to design a process, such as food handling standard. And following standards provides senior engineers some legal safety when approving designs, because they can reference the standard as a way that something is the acceptable method to do something, just as going outside the standard can sometimes incur further legal risk. And then you have the sharing of ideas, because standards help promote best practices. And as I said, ISO, which was formed in 1948, the International Organization for Standardization in Geneva, is really sort of the premier standards body. And there's literally standards for everything. There's standards for gel ink ball pens and refills. There's standards for specifications for caps to reduce asphyxiation. All of your standard computer cables, hex sockets, different screwdrivers. There's almost a standard for anything you can imagine, which is sold in the marketplace. And one of the important things to realize is that standards actually help bring a certain amount of freedom. And they shouldn't be viewed as something that stifles creativity, but something that actually enables creativity. It's a bit counterintuitive to think that you actually have more freedom and flourishing through standardization and specification. But if you consider the rule of law in a country a form of a standard, the reason that you feel safe when you walk down the street is because you're not worried that you're going to be mugged or jumped. And the reason that soccer players are able to play the games is because they all know the standards and specifications of the game. Without rules, there would be no game. Without standards, there's reduced capability of innovation and safety. And so standards make it possible for new companies to get into a marketplace. And there's obvious examples of where this has not gone successful. Although most countries in the world standardized their rail gauge in the 1800s, and this led to a lot of inefficiencies in transportation, not everyone did this, and Australia remains kind of a notorious example of having multiple rail gauges within the same country. And I think the big takeaway here about standards and specifications is that standards create compatibility, safety, and the sharing of ideas to enable efficient and innovative marketplaces. And without them, the complex world we live in would not function. And we come now to the last observation, observation 5. And I think it's important to focus on the end goal and not the technology. So modular systems must be designed to allow for both incremental technological advancements within a single module, as well as the entire replacement of an existing module or set of modules with new modules. For instance, in the case of the printing press on the left or the telephone on the right, each of these undergoes incremental innovations of the technologies, as well as stepwise and logarithmic jumps in innovation. But although printing has gone on for hundreds of years and telephones for at least the last 1.5 centuries, the overall goal of each technology remains the same. And so if you're thinking about designing robust modular systems, understanding how the specific technologies you have now will evolve and change is critical. And therefore, I think focusing on the goal of the modular system you're trying to create is more important than focusing on the one specific technology. So, for instance, the objective of communication in the printed word remains the same, but the specific modules, if you think about what you use to communicate in the printed word, has changed dramatically. Here's some examples of old typewriters, and the typewriters themselves have gone under evolution, and then there was a logarithmic jump when you went from a typewriter to a computer keyboard. You could imagine, for instance, the evolution of listening to music. And you have a certain amount of modularity, whereas before you would connect the music listening device to the music emitting device, or like the amplifier to the speaker, or your phone to your headphones. And then there was a logarithmic jump in the iPhone 7 where the iPhone removed the headphone jack. Now, the objective of listening to music through a speaker system remains the same, but instead of using a cable, all those modular components have been entirely removed from the overarching modular system and been replaced with wireless Bluetooth transmission. You could think about something like music. Music's very modular. You require a score and you require an instrument, and these two large modular components are interfaced by a third module, which is the human. And of course, each of these components can be designed, built, innovated, improved by different people, organizations, and companies. And each one can undergo its own innovation at different points in history. And of course, the different parts of a piano have evolved over time with different types of instruments. The actual process of sheet music itself has evolved over time. And even that human, which is interfacing and joining these two different modules, could be replaced with a synthetic self-playing piano, or some sort of a tapper which hits the keys on the piano. Or you could combine entirely several of these modules together just with a synthetic piece of computer software. So within each of these modules, you can go in and break down the submodularity. So if you think about something such as the actual score and sheet music, you have the modularity of the particular notation and how those different notes come together to create different octaves and standard scales. You have the modularity of the actual page that the notation is printed on, which is going to be a standard probably sheet of paper. There's ink on that sheet of paper, which is standardized, which comes in through printers. This all fits together in the physical world. And so when designing a modular system, really think about your end goal first. What is the objective of the system that you're trying to create? And then you block off in very large categories the large thematic modules you need to get there. And then within these large thematic categories, you put the specific technologies at the time and more specific details, because you're anticipating that there's going to be upgrades and changes and progression within each module, and then over time, large modules might merge or be swapped. But if you start with the end goal, you'll be able to build a system which is robust enough to handle the evolution of technology. And of course, these are 5 principles from the physical world regarding modularity. I'm sure there's many more. I found that these have been helpful in trying to understand how to design digital modularity. So understanding how to design modularity in the software systems for electronic healthcare records. And I think there's a lot of things we can bring from these types of principles in the physical world into our digital constructs. All the images attributed in this presentation can be found at the link in the blog post below. And you can read more at gregoryschmidt.ca.